Hello, everybody. My name is Sophia Wong, and I'm an assistant professor of ophthalmology at the Byers Eye Institute at Stanford University. Today, I'll be talking about gaining the necessary skills to work with big data. I have no disclosures. The purpose of this talk is to describe 3 progressive key skill set areas that are needed for working with big data and why they're important. I'll cover understanding databases and SQL, programming for reproducible science, and briefly touch upon cloud computing. I'll describe considerations in deciding how to gain these skills, and importantly, I'll point out some resources that I've found helpful over the years for gaining these skills. Who is this talk intended for? This talk is pitched at folks who may be at the beginning of their journey in learning how to work with large-scale data sets. Maybe you're saying to yourself, I've never worked with any data that's bigger than an Excel sheet. Or you think, I have a research question and I want to see if I can answer this question using one of the large databases out there, such as insurance claims or national survey data. Or maybe you want to learn to do your own data analysis and don't know where to start. So I'll dive right in to the first part, which is understanding databases. And I want to start with a recent real-world example of what happens when your data won't fit in Excel anymore. At the beginning of October, the Public Health Service in England discovered that they had failed to report almost 16,000 COVID cases to the national dashboard. When they identified the missing cases, the surge they were going through became even more apparent. And the problem was due to how they were collating the case data that was being provided to them by the testing firms. They received the results in comma-separated text files, which they then imported into Excel before uploading to their dashboard. And unbeknownst to them, the Excel template they used could only handle 65,000 rows of data, which was only 14,000 cases worth of data. So the extra cases beyond that just got cut off and dropped out of their data pipeline. The impact of this error wasn't just loss of data. The contact tracing process was delayed for these missing cases because they didn't know that they were COVID positive. So they could have been going around spreading COVID, making the surge even worse. So what was their fix? Maybe a new, robust database system? No, they're now breaking up their test results into smaller batches so that they won't hit the Excel row limit. And my guess is it's just too difficult right now to redesign their data pipeline on the fly to streamline the process. So that highlights even more why you have to store your data properly from the beginning, and serves to illustrate why the big data that you want to work with is not stored in a single Excel-like table. Now, when you're working with data that other people have already collected, one of the first tasks that you're faced with is how to cut your cohort. That is, find the population of patients that you're interested in for your particular research study. And you'll probably have a list of inclusion criteria or exclusion criteria. And at the patient level, this might depend on demographic features. Maybe you want them to have a particular diagnosis or a particular procedure. Maybe you want particular medication exposures or lab values or other characteristics. And the overlap of all these criteria defines your cohort. In a typical large dataset, all these criteria are stored in different separate tables. Here's an example database architecture from the Optum Data Warehouse, which is an insurance claims database. You can see that we have demographics and administrative data in one table, which is one row per patient. And then you have diagnoses and encounters in separate tables, one row per encounter or one row per diagnosis. And then meds in another table, one row per pharmacy claim. Labs as well in a separate table, one row per test. So the key to defining your cohort is to be able to retrieve the disparate pieces of data that you need corresponding to your list of inclusion and exclusion criteria and match them up between potentially many separate tables to form your own data sets that you can use to analyze. The programming language to do this with is SQL, or Structured Query Language. This is a language of the relational database, which is so called because the tables in the database are related to each other in specific schemes. Even if you never learn SQL to do this, supposing you cut your cohort with some other mechanism or language, no matter how you cut your cohort in the end, you have to understand how a relational database works, how the tables are organized, what are the keys or the identifiers of the tables, how to link different tables. You'll need to understand basic operations like different ways of joining tables, deduplicating entries, filtering the rows of the tables according to some criteria, selecting columns, or creating new variables of interest, and so on. So here are some suggestions for how to learn about database structures and perhaps some SQL as well. I do want to emphasize that you should first of all read the sometimes extensive documentation of your chosen data set. And there's a wealth of information in there about all the different tables available and what's in them and what are their keys or IDs that identify the rows of the tables and how they're related to each other. And I've highlighted some resources here from LinkedIn Learning, which you might have access to through your institution. I like these tutorials because they're relatively short and can be done in a few hours or spaced over a few days. So they're a little bit low commitment and high yield. The one on the left is a good overview of relational databases, and the one on the right dives into actual programming in SQL. So now we'll move on to the second set of skills, which is important for data analysis. This is the fun part. You've got your cohort. Now what do you need to do? First off, there's often a lot of data cleanup that you might still need to do. You might need to define some variables like a composite outcome variable, such as successful glaucoma surgery defined by IOP lowering of 20% or more from baseline, or stopped a glaucoma medication. So you have to create all those variables that you might need for your project. Secondly, you have to actually run the analyses, and this might be inferential analyses, where you do traditional statistics and look for significant predictors of some outcome using regression or survival analyses, or you might want to build some sort of machine learning predictive algorithm. And then when you're done with all your data preparation, you might then wonder why you shouldn't just import your data into Prism or SPSS and point and click your way through the analyses. I'll tell you why that's not a great idea. Here's a typical graphical user interface for a statistics program. You import your data and then find your desired analysis in a drop-down menu. Looks easy. But there are often software technical limitations. You might be limited in working with one table at a time, where your data might be in multiple tables. There might be limitations on how many rows or columns your data can have. But the worst thing is after you point and click your way through the analyses, putting in all the checkboxes for the different kinds of options, there might be no good record of exactly what you did. What if you or someone else has to replicate these analyses 9 months later after you get a reviewer's feedback on your manuscript? It could be a nightmare to duplicate. And it's very inefficient. Say you're checking univariate analyses with 25 predictors against your outcome, and then say you have to go back and tweak one setting and run all 25 analyses again. Those clicks can add up very quickly. So you really need to do the analysis in a reproducible, well-documented, and efficient way. You need to do some programming, and to document those programs and save the results so that you or anyone else can run them over and over. That is programming for reproducible science, and it's a philosophy that guides the whole approach towards saving not just the programs, but the data files and everything associated with your project in a way that's easy to understand and replicate. Just like how we have physical lab notebooks for documenting bench experiments, in data analyses, we can use programming notebooks interfaces, such as Jupyter Notebooks, to document your data analysis experiments. You can put your code into little executable cells and then run the cells individually and save the outputs, which might be outputs of regressions, or they might be graphs or other results. Another important must-have for reproducible science is good workflow hygiene. So we've all been here in this situation in the comic on the left. You might have multiple versions of files that multiple team members were working on, and you can't tell which is the latest. Or maybe you have the latest changes that are spread across multiple files. That's not the end of the world for a manuscript or a budget, but you really don't want to be working off the wrong version of data. This could send you and your collaborators on a very long, tedious, and unnecessary bug hunting expedition when your results don't quite match up or look right. So you should save all your research products in an organized, consistent, and understandable way, and keep good documentation of how you made your new variables and why, and how you did your analyses and what decisions you made during that process and why. And maybe it should go without saying that you should never save a file as final or last version, in case there's another version after that. A big part of good data analysis hygiene is having some sort of version control system for your code. The standard version control system used now is called Git, which you can access through the GitHub client. Git keeps track of different versions of code for you, which is very helpful if you need to revert to some earlier version after making an edit that breaks something. It's pretty much essential if you have multiple coders on the same project so that you can work on the same files. And it's also a good place to document your code with README files and such, so that you don't have the situation in this bottom panel where someone has to look at your code several years later and has no idea what you did. So I would highly suggest learning some basics of GitHub, and would say that it is required if you are or will be collaborating with another programmer for a project. For folks who are new to GitHub, there is a relatively easy desktop client that can be used. Okay, so programming for reproducible science requires some way of 1, documenting the results, 2, good workflow hygiene, and 3, version control. But what about the actual analyses? What language should you learn to get those analyses done? Most people have limited time and energy and have to pick somewhere to start. So first and foremost, I would suggest learning whatever your group or community is using. If someone else in your group is using R and has example code that they can bequeath you in R, then learn R. Don't go it alone if you don't have to. Learning from other people's code is highly valuable. But sometimes you have a choice because you're starting some project de novo. So here are some different widely used programming languages that you might be considering and what they can do. So Stata is a statistical programming package that has the advantage of being relatively easy and friendly to learn from scratch. You can do any kind of traditional statistics or epidemiological studies in it. You can buy different versions that can handle different sizes of data for different prices. To be sure, though, all your data has to fit into your computer memory, so whatever version of Stata you get will still be limited by your available memory. It was my first language, and you can get very far on Stata. SAS is often considered a traditional industry standard, so that's a plus. It's also great at doing any kind of traditional inferential statistics. I think it's much harder to learn from scratch. It's also a lot more expensive if you don't already have institutional access. It can, though, handle very large data sets. It doesn't read them all off your hard drive into memory at once, so that's a positive. And then there's R. So R is rapidly becoming a widespread industry standard because it's free and open source. And so if you're just starting and have no previous preferences and are not sure what kind of analysis you want to do, R is a great place to start. I would say it's intermediate in difficulty to learn from scratch, but there are lots of free tutorials and courses. There's also many packages that have been written for R that extend its native capabilities to do fancy or cutting-edge analyses. It does all the traditional inferential analyses. There are also many machine learning packages written for it, so it's very versatile at doing that too. It's not really a standard, though, for doing deep learning, so I wouldn't recommend it for that. And another limitation is that your data sets and objects will also be limited by the size of your computer memory. And finally, there's Python. It's also rapidly becoming an industry standard for data analyses. And it's similar to R in difficulty for learning. There are some packages that can help you do inferential statistics in Python, but really they're just not as good as the other options like R. Python really shines in doing machine learning, deep learning, and being very versatile so that you can work with different kinds of data types like text also, or images, and not just numbers. So if your primary interest is in machine learning or deep learning, I would definitely recommend starting with Python. So I'll breeze through some resources for the different programming languages. You can always look up any of the details of these later if you're interested. For Stata, I just want to highlight this amazing book on the left. Whether you're an old pro or a newbie at Stata, this book is an absolute must-have because it goes through so many useful practices for efficient programming and good data hygiene practices. I've also linked some online resources and step-by-step tutorials that you can check out later. For SAS, I like Ron Cody's books, particularly this one on the left, which is like a cookbook. It's full of example code for doing all kinds of different data manipulations. For R, all these books are freely available online. The free online R for Data Science book is a good practical introduction, covers the important packages. For a little bit more theoretical underpinnings, the Introduction to Statistical Learning is great. It's not too overwhelming. And for a deeper and more detailed version, there's this one on the right, The Elements of Statistical Learning. That's really good for reference. For Python, I definitely recommend Coursera. So these are two courses that are run by professors from the University of Michigan. Python for everybody assumes zero programming background, but even if you know a little programming, it's pretty useful and practical. After that one, there's this one on the right, Applied Data Science with Python, that covers a lot of important must-know Python packages for data science and analysis and visualization. The third and last point that I will just touch upon is cloud computing. We need this when our data gets big, not just too big to fit into Excel, but too big to fit into one computer. With cloud computing, you can easily scale up your storage, memory, or processing resources and do collaboration with multiple users, and all of it in a secure environment. It's usually much cheaper to rent cloud computing resources than buying your own supercomputer. How you access cloud computing resources is through SSH, or Secure Shell. And you might already be used to connecting to other desktops using Remote Desktop Client, where you remote into another computer, you can see the other computer's desktop and open their applications, all from your own computer. SSH is sort of similar in concept, except there's often no desktop to look at per se. Instead, you type in your commands on your own command line, and that allows you to connect to the other computers and then run the commands on the other computer's command line. The most common platforms for cloud computing are Amazon Web Services or Google Cloud Platform. Your own institution might have their own servers, and so I've just linked a few useful tutorials here. If you want to test out cloud computing for cheap and easy, my secret weapon is Google Colab. This is a free level of resource that doesn't require any fancy setup. You can immediately run Python with a Jupyter Notebook interface. It's great for small experiments that just need a little extra boost in memory or processing power. So that's the end of my talk, and hopefully I've given you all a starting point that can jumpstart your process towards working with big data. And I hope that you find these resources to be useful.